All right, good afternoon, everybody. Welcome to our last day of class together. Woohoo, we made it. So today we are just going to go through kind of the highlights of everything that we talked about. So we'll go through a couple of key concepts, key vocab terms, key equations for chapters 1 through 12, which are the 12 chapters that we were able to cover. And then we'll go through some example problems at the end that combine concepts from multiple chapters together. So these would be like final exam or midterm exam quite type questions where they're pulling information and concepts from multiple chapters at the same time and seeing what you can do with them. So I hope that this is a helpful review for you guys. I hope that this class as a whole has been helpful for you. If you have any feedback, please do let me know. I'm always open to feedback because I always want to get better. So yeah, let me know if there are things that I can do better. Um, and if you haven't done so already, please make sure that you take that post test that is posted on Canvas. Will the PDF for this review session also be posted on Canvas? Yes, it will be. I'll be posting this PowerPoint PDF on Canvas after class today. And then the video link will also be there. I'll make sure that once this video is posted to YouTube, the link is there so you can go back and watch this recording at your leisure. I'm not exactly sure when you will lose access to our Canvas class. Um, if you even will lose access to our Canvas class. Some classes remain open just forever, basically, and some classes like close their access after a certain amount of time. So, um, if any of these resources have been helpful to you, maybe take a couple minutes, download them, save them somewhere on your computer so that you can access them again later. Anywho, let's get going. Chapter one, wow, way back 6 weeks ago. So chapter one was all about like the foundations of science in general. So things like units, unit conversions, um, metric prefixes, how to convert between different types of prefixes, all that stuff. That was chapter one. So, some important things from chapter one: units must be consistent within a problem. If we're trying to add together two things, we can't add together apples plus oranges, right? It has to be apples plus apples. So, our units in an equation matter. And we've seen as we've gone through this class that some of the constants that we use, for example, the acceleration due to gravity, constant, more or less, as 9.8 meters per second squared when you're close to Earth. Universal gravitational constant, 6.67 times 10 to the negative 11. Those constants have specific units related to them. And if you don't use those specific units in the rest of your equation, then that constant, like, it doesn't work, right? We need our units to all be the same in order to do our math correctly. So make sure that you are kind of familiar with what variables correspond to what units. So for example, how do you measure the speed of something? Like what units would you use for speed? Well, speed is how much distance you cover in a certain amount of time. So that would be some distance unit over a time unit. Usually we use meters per second. Um, Things like, oh, what do you measure mass with? If you're given something in kilograms, is that a mass or is that a weight? So be able to know those types of things, what variables use which units. And that will really help you if you forget an equation, you'll be able to kind of derive an equation based off of just units. When we're dealing with really big or really small numbers, best practice is to use scientific notation. So even that gravitational constant that I mentioned to you, 6.67 times 10 to the negative 11, that's scientific notation, right? It's just a way to shorten these really long numbers, whether they're big or small. And so when we're writing something in scientific notation, we put the decimal point right after the first non-zero digit. So 6.67 6.67. And then we drop the following zeros if they are not significant. So that initial number, the one before the decimal point, that's called your coefficient. Along with any other decimal places that might correspond with that. For example, 6.67, that's considered your coefficient. Then we take our coefficient and multiply that by 10, so 6.67 times 10. And then to figure out our exponent, we count the number of places from the decimal where it was originally to where we put it to get it behind that non-zero digit. So if we had to move the decimal to the left, that means our exponent is positive. We took a really big number and made it shorter. If we took that decimal place and we moved it to the right, so there were zeros that we had to get rid of in front of the number, that means the exponent is negative. So we were dealing with a really small number. So 6.67 times 10 to the negative 11 means it's a very, very small number because that exponent is negative 11. Get to know your metric prefixes. So I listed there the main 3 that you use in Physics 1. However, there are quite a few more prefixes that you will encounter in physics. So kilo, which is lowercase k, is times 10 to the 3, or 1,000 of your base unit. Kilometers is 1,000 meters. Kilograms is 1,000 grams. Centi, or lowercase c, is times 10 to the negative 2, so that's 100th. And then milli, lowercase m, is 1,000th. Right, so those would take smaller portions of our base unit. So 100th of a meter is a centimeter, and 1,000th of a meter is a millimeter. Right, so these prefixes, it can really help you. You will be required to memorize them. They will not be given to you on a test or anything like that. So it can help in your memorization if you can find similar words that use the same prefix. Like centipede is a bug that has 100 legs, right? And a centi is 100th. Century, right? 100 years. Cents, there are 100 cents in a dollar. For milli, a millennium is 1,000 years. So try to think of some additional words like that that might help you just kind of remember these things. Micro is another one that's commonly used. That's times 10 to the negative 6, and that has the prefix mu, that Greek letter mu. Nano can also be somewhat commonly used, more so in physics 2, when you're dealing with like really small electrical charges. But nano would be times 10 to the negative 9, nano negative 9, and it's a lowercase n. Okay. And then when we're converting between units, whether we're going from metric to metric or from English to metric or whatever unit conversion we need to do, my favorite way to do that is to set up ratios. We saw an example of that on Tuesday where we were setting up ratios. And when you do that, if you have a unit on top, in the next fraction, you'll want that same unit on the bottom, so that the unit on top and the unit on the bottom will cancel each other out. And now we've arrived at a new unit. You can set up as long of a chain of ratios as you need to in order to get your units to where they need to be. Right? And then all of the numbers that are on top of your ratio, you would multiply. And then any numbers that are on the bottom of your ratio, you would divide. Right? So if you want to see examples of that, check out the resources that I posted for chapter 1, those chapter 1 notes, those unit conversion practice sheets, all that jazz. Also covered in chapter 1 were vectors and scalars. So remember, a scalar is a quantity that just has a size associated with it. Scalar size or magnitude. So these would be things like time, mass, speed, temperature, energy. These things don't have a direction, right? You can't go like forward 4 kilograms like that. It doesn't make sense. It's not necessary. So when we're dealing with a quantity that just has a size to it, that's a scalar. Vectors, on the other hand, are quantities that have a size, a magnitude, and a direction, right? So if speed tells us how fast we're going, velocity tells us how fast we're going in a certain direction, right? So speed would be our scalar, velocity would be our vector. If distance tells us how far we've gone from our starting, well, how far we've gone total, then displacement would tell you how far you've gone from your starting point, right? So that would be our vector, whereas distance would be our scalar, okay? Some important vectors that we've used, of course, displacement and velocity I just mentioned, but also acceleration, force, momentum, torque, which we didn't really get to talk about a whole lot. But anything where the direction matters, that would be a vector. And vector math is a little bit more complicated than scalar math. We can't just add the numbers and call it a day all the time. Sometimes we can. But with vectors, we need to take into account which direction they are going. So, for example, right, um, if we travel 4 meters to the right and then 5 meters to the left, the total distance that we've traveled is 4 plus 5, so 9 meters. Our displacement, though, is -1 meter because we went 4 meters this way and then 5 meters back this way past our starting point by 1 meter. So -1 meters would be our displacement, even though our distance is 9 meters. Now, usually with a vector, we represent it as an arrow because that shows us both a length, the magnitude, and the direction. And when we're adding vectors graphically, so drawing them out as arrows, you can take that arrow and slide it around anywhere you want it to go, as long as you don't change the size or the direction, right? Because those are the important things for a vector. If you change one of those, you've changed the whole vector. So we can slide two vectors together so that they meet tip to tail, as long as we don't change those aspects about them. And so sometimes, if we're adding two vectors, that'll make a really nice triangle. And then you'll see your resultant, maybe it's displacement vector. Your resultant vector is the completing the triangle vector. But you can do this process for as many vectors as you have. You just take the first one, well, take the second one, slide it onto the first one, tip to tail. Take the third one, slide it onto the second one, tip to tail, and just create this chain of vectors, as many vectors as you have. So that would be how we do it graphically. Sometimes it's much easier to do it mathematically, though. And so when we're adding vectors mathematically, we break them down into their components. So we look at how far in the x direction the vector is going compared to how far in the y direction the vector is going. And we keep those two directions separate from each other, right? The x direction and the y direction are independent, they are separate from each other. So when we're breaking these vectors down into their components, we use SOHCAHTOA or our trig functions, to figure out the magnitudes in each direction. Right, so here's our triangle down here. This hypotenuse line would be our vector. And if we want to figure out the x component of the vector, that would be this side down here, the side that's in the x direction, according to our typical coordinate system at our typical graphing axes. So since this is our angle right here, and this side, the x side of the triangle, is adjacent or next to our angle, we would use the cosine function because that combines adjacent over hypotenuse. Right? If we were looking for the y component, typically we would use the sine function because that's the side opposite our angle over our hypotenuse. Now, we do have to be careful. We can't just assume that the x direction is always going to be cosine and the y component is always going to be sine. It depends on the scenario. So that's why I always recommend that you draw a picture of your scenario first so that you can see what's happening, see, especially with forces, see which direction different forces are pulling, and then you can start breaking down your vectors from there. Okay. The magnitude of a vector is the size of the vector. So if we're given, or if we calculate the components of the vector, the x component and the y component, we can use the Pythagorean theorem to figure out the magnitude of our vector. We can figure out the direction of our vector then, this angle, using the inverse tangent of the y component over the x component. Okay, so that's chapter 1. Whew, lots of foundational things. Hopefully you see, like looking back at this chapter, how important all of this foundational work was for later chapters. Chapter 2 was our introduction into motion. And so when we're dealing with motion, whether it's in one direction or multiple dimensions at the same time, it's essential that we establish a coordinate system. Now we can make this coordinate system pretty much however we want to, unless it's defined for us. But we can locate our origin wherever it's most convenient. We can pick which directions are positive and negative. Typically, right and up are positive, whereas down and left are negative. But if that's not the most convenient case for your scenario, then you can change it as long as you keep it consistent throughout the entire problem. Okay, so define the coordinate system however you wish. Keep in mind, though, that some are more useful and some are more typical than others. If we draw a vector from the origin of our coordinate system to the place where an object is located, that would tell us the object's position. And whenever that position is changing, that tells us the displacement, the change in its position with respect to the origin. Remember, displacement is a vector, so it has both a direction and a magnitude. Right. Velocity, we talked about just a minute ago how that's a vector, right? It has a direction and a magnitude, and that tells us how fast the object is moving in a certain direction, right? That means how much distance, I suppose, how much displacement it has in how much time it's been moving, right? So if the object is starting at the origin, and it takes 2 hours on its journey and comes back to the origin, its displacement is 0, no matter what amount of time it took to do that. And so its average velocity then is 0. No matter how fast it went on its journey, if its displacement was 0, the average velocity is 0. Now, we talked about different types of velocity too. Average velocity, instantaneous velocity, which is the velocity at a particular moment in time. And that particular moment in time can involve calculus. We'll see that on the next slide in just a minute. But there can be simpler ways to do it if you don't know calculus. Okay. So an object's position, constant average velocity, and time are related to each other using this, sometimes it's called the DIRT equation. Distance is rate times time, but it's written out here in this way. Distance equals velocity times time plus its initial position. Okay. So here, this stack of graphs that we saw in probably week 2, the end of week 1, week 2, this is our visual representation of motion, right? So position, velocity, and acceleration are all related to each other mathematically and graphically, right? Acceleration tells us how the velocity of an object is changing over time. So that's delta V. Remember, delta means the change in something. So the final velocity minus the initial velocity. divided by the change in time. And there are really three ways that an object can accelerate. It can speed up or slow down because that changes the magnitude, or it can change direction because that changes the direction, right? And acceleration and velocity are both vectors. Magnitude and direction are important. So those three ways are the ways that we can accelerate: speed up, slow down, or change direction. If we compare the velocity and the acceleration, their signs, we can know what the object is doing, right? So if velocity and acceleration have the same sign, if they're both positive or if they're both negative, then the object is speeding up. If they're both positive, that means it's speeding up in the positive direction, so forward or up or right, something like that. And if they're both negative, then it's speeding up in a negative direction, so maybe backwards or down. If those two have opposite signs, so one is positive, the other is negative, let's say velocity is positive, but acceleration is negative, that means the object is moving forward, but slowing down. If the velocity is negative, but the acceleration is positive, that means it's moving backwards and yeah. So look at the sign to compare what this object is doing. Is it speeding up? Is it slowing down? What's happening? Check out the signs of those two. Sorry, my daughter was like jiggling the doorknob and I lost my train of thought for a second. Anyway, these motion graphs are related to each other. Okay, so velocity is the slope, or the calculus word derivative, of a position time graph. So if we take the slope of a line, possibly a tangent line, which touches the curve at just one point. So take the slope of the tangent line, and that will tell us about the velocity. And similarly, acceleration is the slope or the derivative of a velocity time graph, right? So as we try to figure out how these things are related to each other, sometimes it helps holding up your finger or a pen or pencil, just kind of hold it up along the curve and see what happens to the slope of that line. And that will tell you a lot of important information. So if we look at this position time graph, that top graph, right? It starts off with a positive slope that gets shallower and shallower to zero at the middle. Remember, the slope of a horizontal line is zero. And then it gets steeper and steeper negatively as it goes the rest of the graph. So that's why in our velocity time graph, we see it starts with a positive that gets closer and closer to zero, and then it gets more and more negative as we go. If we take a look at that velocity graph, it is a constant negative slope. And so our acceleration is a constant negative number. Okay, so take the slope of the line to figure out what information we can about the velocity from position, or figure out the acceleration from velocity. They are related to each other. Now, mathematically, calculusly, if we're doing the derivatives, there were a few derivative rules that I taught you guys. The most important, I would say, being the power rule. So remember, for the power rule, we multiply the coefficient by the exponent and then subtract 1 from the exponent. So this is how we write a derivative, d over d something, right? And this something here, this variable, tells us which variable we are taking the derivative with respect to. So in this case, we're taking it with respect to time. And here's our function, t to the fifth. So the coefficient of this is 1, right? 1 times t to the fifth. So we multiply the coefficient 1 by the exponent 5. That becomes our new coefficient. And then we subtract 1 from the exponent. So 5 minus 1 is 4. So our derivative of t to the fifth is 5t to the fourth. That's the power rule. These graphs are related to each other in another way too, and that's going up the stack of curves. So if we know about the acceleration, we can figure out the velocity. And if we know about the velocity, we can figure out the displacement by taking the area under the curve, or the integral. Integral is the calculus way to say that. Now, remember, this terminology is a little bit misleading. Area under the curve actually means the area between the curve and the x-axis. So that means that our area can be positive if it's above the x-axis, or it can be negative if it's below the x-axis. So here in this velocity time graph, you can see this first chunk has a positive area, and this second chunk has a negative area, and it is totally fine to have negative areas in calculus. It hurts my soul a little bit, but it's totally fine to do that. Okay. So integrals you'll learn more about in calculus 2, but I just wanted to introduce those to you a little bit. All right, chapter 3, again, motion, but now in multiple dimensions at the same time, sometimes called projectile motion. So with motion that has a constant acceleration, the relationships between position, velocity, acceleration, and time, those are called the kinematic equations. Remember, kinematic means of motion. So these are the equations of motion. And these equations work in either direction. We just would replace x with y. And they are connected to each other by time, right? So we can just look at the x direction and separately just look at the y direction, because remember, x and y are independent of each other. Our motion horizontally does not affect our motion vertically. The only common variable that those two directions have is time, right? So we can treat these problems by looking at one direction at a time. And then once we've gotten all that information, let's say for the x direction, we can use time as that linking factor to find our information in the y direction, or vice versa. Okay. So these are a couple of our kinematic equations that we mentioned. The rest are outlined there for you in chapter 3. So our average acceleration due to gravity on Earth, which we say is a constant, we call it little g, and it's a vector, right? Acceleration is a vector, so we give it a bold g, is approximately 9.8 meters per second squared downward. Okay, it's independent of mass. It's just an acceleration. And so when we ignore air resistance, we get this nice parabolic sort of motion. Um, Hopefully you guys remember, if we don't ignore air resistance, then our motion no longer is nice and parabolic. It drops off really rapidly. It does not go as far. It does not go as high, all that stuff. Free fall is our motion when only gravity is acting on you. So this is an idealized case, ignoring air resistance. The only force that's acting on the object is gravity pulling it down to the center of Earth. So let's think about this picture here quickly, right? Let's say that this is a ball that we threw in the air. Maybe you're playing catch or something like that. So just at the peak of this ball's trajectory, its pathway as it flies through the air, the velocity in the y direction is momentarily, instantaneously 0, because it's changing direction from positive to negative. And so in the y direction, vertically, it is momentarily 0 velocity. It can still be traveling sideways and have a non-zero x velocity, but vertically its velocity will be 0. However, the acceleration will not be 0, because if the acceleration were 0 and the ball is at the top, it would not move again, right? Acceleration tells us how the velocity is changing. So if there's no acceleration, there's no change in the velocity, it would reach the top, hit 0, not change again, and the ball would just hover there. So it is definitely possible to have a 0 velocity and a non-zero acceleration. It happens very frequently. Right. And then this last point really quickly here, a bullet dropped and a bullet fired horizontally from the same height hit the ground at the same time. Remember, horizontal motion and vertical motion do not affect each other. So even though the bullet fired horizontally has horizontal motion, gravity does not pull something horizontally, it pulls it vertically from our reference point. So since gravity is pulling on both of these bullets in the same way, they will both hit the ground at the same time. Okay. Chapters 4 and 5, this was Newton's laws and forces. An object that experiences a push or a pull has a force that is exerted on it. Okay, we talked about all kinds of different forces, which I'll show you quickly soon. But remember, force is a vector. It has a direction and a magnitude. And we have two different kinds of forces. We have contact forces, where objects must be touching each other in order for that force to exist. And then we have field forces, where the objects don't need to touch each other. So a contact force might be friction, right? Your hands need to touch each other to rub together and create that heat from friction. Whereas gravity is a field force. We don't need to be touching the sun in order for Earth to orbit around the sun due to gravity. Luckily, because that would be a bad day if we had to touch the sun. A free body diagram is a picture that shows all of the forces acting on an object in the direction that they are acting and to scale as best as you can, right? So we want to label all of those forces. We want to make sure that all of those forces are pointing out from the object, which we usually represent as a box or a dot or some simple shape like that. And then once we have that picture drawn, it's a lot easier for us to break down any forces that might be on angles into their components, to visualize the net force, to see what's happening in the scenario. Free body diagrams are just very helpful tools. So we can use vector addition to add forces together. But again, we keep the x component or the x direction and the y direction separate from each other. So we add y and y. We can add x and x. We do not add x and y. Okay, so the net force is kind of our leftover or unbalanced force that's acting on an object. If there is no net force on an object, that means all of the forces are balanced by something. So the x forces are balanced. The y forces might be differently balanced, but they're balanced by each other. So no net force means the object is in equilibrium. And we'll see in chapter 11 different kinds of equilibrium. But equilibrium basically just means there's no acceleration. Right? It will either be at rest or it could be moving at a constant velocity, right? Constant speed, constant direction. But it just won't be accelerating. The motion will not change if there's no net force. When objects are falling, they accelerate until the force of gravity pulling down is balanced by the air resistance or the drag force pushing up. Once those two forces are balanced, it cannot accelerate anymore because there is no net force acting on that object. And so it will fall at a constant speed, which is called terminal velocity. And terminal velocity depends on the object's shape, its surface area, more so than its mass. So Newton's three laws of motion. The first law we call the law of inertia. That tells us that an object at rest tends to stay at rest, and an object in motion tends to stay in motion in a straight line at a constant speed, unless there is some unbalanced force that acts on it, some net force. So basically, an object's going to keep doing what it was already doing unless something makes that motion change. Inertia, we call it law of inertia. So inertia is the tendency of an object to resist changing its motion, not necessarily to resist motion, just to resist changing its motion. Right? The more mass an object has, the more inertia it has. So I gave the example of trying to push a train to make it start moving. So the train is stopped. You are pushing as hard as you possibly can. It is going to be very difficult to make that train start moving, to change its motion from rest to moving is very, very difficult to do because it has so much mass. Right? If I try to push my phone off the table, that's a lot easier to do than pushing a train because my phone is much less massive. However, if the train is already moving, it's very difficult to make it stop moving, right? Changing its motion. Change is the key there. Newton's second law, the law of force and acceleration, or F equals ma, tells us that the net force on an object is directly proportional to its acceleration. So if there is a large net force on an object, there will be a large acceleration. The acceleration is inversely proportional to its mass. Right? So if it has a large mass, it will have a small acceleration for a given net force. Newton's third law is also called the law of action reaction, and it tells us for every action force, there's an equal and opposite reaction force. So remember, reaction is not the same thing as a result. A reaction is a force that is equal in magnitude and opposite in direction. Right? So the equation here, the force of object A on object B is the same size as the force of object B on object A, just in the opposite direction, right? So we gave a bunch of examples of like from The Office. So Andy punching the wall, for example, the force that his hand exerts on the wall is the same size as the force the wall exerts back onto his hand, right? And the reason the wall breaks, and likely not his hand, although maybe his hand broke, I don't know, is because the wall just cannot withstand that amount of force. Okay, so here is our chart of the most common forces that you'll see in Physics 1. Gravity, also called weight. The equation over there is mass times g. We have the normal force, which is a support force. Remember, normal just means perpendicular. So perpendicular to the surface. This would be anytime an object is sitting on a surface or leaning on a surface, like leaning on the wall. And so usually this normal force is equal in magnitude to the weight, unless we're dealing with a case where we're on an angle, like a ramp, or if we're like leaning onto the wall, then it won't be equal to the weight. It would be equal to the force that you are the force that you are pushing onto the wall. Friction is another common force. It has an equation. Remember, there are different kinds of friction. There's kinetic and static friction, but they both have this very similar equation. Friction equals mu, that coefficient of friction, which tells us how slippery the surface is, times the normal force. Remember, with mu, the closer it is to 0, the more slippery the surface is. And it's almost always a decimal between 0 and 1. Mu can be bigger than 1, for example, with Velcro, but that would be the case where it's easier to just pull it apart and move it physically than it would be to try to slide it. Tension is whenever we have some kind of rope or string or wire attached to our object that is being pulled. There's really not an equation to calculate that. It would be given to you in the problem. Air resistance, again, we typically ignore air resistance in Physics 1. I did give you some equations for it in the PowerPoint slides, but we don't really use it in Physics 1, so I just didn't put the equations there. Any other force that is applied to the object, like your push on the object, for example, is just called an applied force. So that would be based on the scenario. There's not really an equation for it. And then the net force isn't necessarily something that we would draw into a free body diagram, but remember, that's the vector sum of the forces that are acting on the object. So taking into account their direction, right, x with x, y with y, we just add them together, keeping in mind their direction, and we can come up with the net force. All right, chapter 6, we talked about work and energy. So work is energy that's added to a system by some kind of force. And here we see our equation for it. W, work, equals F dot D. This is a dot product. This is not a multiplication sign. So a dot product shows us how parallel things are to each other, how much in the same direction they are. Right? So if our force and our displacement are in the same direction, that means all of the work that all of the force that we are putting on the object goes to move it in that direction of the displacement. But we can also have work that's negative, right? If we're pushing in the opposite direction of the displacement. So for example, friction, since that acts in the direction opposing motion, is a negative work. It kind of takes energy out of the system. So we need to keep in mind the direction of the force, the direction that the object is moving, and the angle between those things if they're not in the same direction. All right, so we can have positive work, we can have negative work, or we can have zero work. If the force is perpendicular to the motion, then it is not, it's just not pertaining to the motion at all, right? So if we're carrying a stack of books moving sideways, or I guess moving forward, um, your normal force, the force that you're using to support those books, is upward. And that's not pertaining to your motion forwards. So that normal force, the work done by that normal force is zero. Okay. Kinetic energy is related to work through this work energy theorem. And kinetic energy, remember, is the energy that something has when it's moving. So kinetic energy, K, is 1/2 mass times speed squared. Kinetic energy will never be negative, and it will be zero when the object is at rest. So work is related to kinetic energy through that work energy theorem that tells us that the total work done equals the change in kinetic energy. So when our work is positive, the kinetic energy increases and the particle moves faster, or the object moves faster. If the total work is negative, then the kinetic energy is decreasing, and so the object is slowing down. And if the total work is zero, kinetic energy is constant, and so our speed is not changing. Related to work, again, is another thing called power, which tells us how quickly work is done. And so that is the work divided by the change in time is our average power. We can also relate that to energy, because remember, work and energy are related to each other. So the change in energy over the change in time. Okay. We also know that work is related to the force and the displacement. So we can see the force, those two lines there mean the parallel force. So the force that's in the direction of the displacement times the displacement divided by the time that it takes. And that's also equal to the parallel force times the velocity. So there are lots of different ways to calculate power, but basically it just tells us how fast that work is done. Chapter 7, more forms of energy. We talked about gravitational potential energy, or the energy that something has due to its position. So when something is raised up above the ground, it has the potential to fall back down to the ground because of gravity. Right? So again, this equation we now know only pertains to situations that are close to the surface of Earth, so within our atmosphere, for example. So this potential energy, U sub G, because there are other kinds of potential energy. So this gravitational potential energy is mass times our acceleration due to gravity times the height above our reference point. You can choose that zero height to be wherever you want, wherever's the most convenient, because it's really the change in the height that we're interested in. Okay. And when we add together all the forms of, well, all the forms of energy, but really so far just kinetic and gravitational potential energy, we usually just call this capital E, which means the total mechanical energy. So we need to keep in mind too that a lot of, well, energy is conserved. Okay. The total amount of energy in a system is always going to stay the same. It may change forms from kinetic to potential, or potential to kinetic, or even to um, heat. Work due to friction can turn energy into heat, but it's never created or destroyed. It only changes forms. We also talked about energy due to springs, which is very similar in its equation to kinetic energy, right? We see that 1/2 kx squared, which is very similar to 1/2 mv squared. So that will tell us how much energy is stored in a spring if it's stretched or compressed, because it has that potential. If you've ever played with springs, they have that potential to snap back into their equilibrium position. Um, so they have energy that are stored in the coils. Chapter 8 about momentum. So we have that equation there for momentum, P equals mv. So P is our variable for momentum, and it depends on the mass of the object and its velocity. Right? And momentum is a vector. The direction matters. The impulse is the product of a net force and the time interval in which it acts. So this impulse, J, is the change in momentum, which is the net force times that time interval. And so since we have this relationship then between impulse and momentum, this is called our impulse momentum theorem. But similarly to energy, total momentum of a system is conserved. It's kept the same the whole time. It is constant. Even though the momentum of each individual object might change, the total amount is going to be the same. So we see there Pi equals Pf. Our initial momentum equals our final momentum. And so now this can definitely be more complicated if you remember momentum examples. The more objects you have, the more complicated it gets to keep track of all of the initial momentums of each object and the final momentums of each object, especially when they're colliding with each other or exploding out from each other. Those are kind of complicated things. So there are several different types of collisions, but in each case, momentum is conserved. So when we're dealing with an elastic collision, two objects, or multiple objects, I should say, bounce off of each other perfectly. And so since they're perfectly bouncing off of each other, there is no change in momentum, there's no change in energy, and so both of those quantities are conserved in those problems. When we're dealing with inelastic collision, that means that objects can bounce, but they don't bounce perfectly. Some of that energy is lost due to sound or heat, or even the materials deforming, like denting, for example. If you get into a car accident and your bumper gets dented, that would be an inelastic collision. So some energy is lost to those kind of external factors. And so that energy that is lost, we call that as work. And if we're dealing with a perfectly inelastic collision, that means the objects hit each other and stick together and move off as one object, one bigger object after that. So that means a lot of the energy to all of the energy is lost. Remember, like transformed into these other things. And so since we have this one object that moves away at the end, the final velocities of both objects are equal to each other because they're now one object. So depending on the particular situation, that will really affect how you set up these problems. Explosions, where you're like starting with one object and you are exploding it into multiple objects, would be kind of like the opposite of a perfectly inelastic collision, right? Because inelastic, we start with many and we end with one. Explosions, we start with one and we end with many. So you can treat explosion problems in a similar but like opposite way, if that makes sense. Like your initial mass is bigger. It's the combination of all the final masses in an explosion. Anyway, so explosions and perfectly inelastic problems are very similar to each other. Chapters 9 and 10, we didn't get a chance to cover in a whole lot of detail. So here's just like a quick introduction to some of these terms and equations so that you have them, I don't want to say all in one place because there are definitely more equations than this. These are the key things again. So if we have a rigid object, so not one that will like stretch or deform, anything like that. So when a rigid object is rotated around an axis, we can describe its coordinate, its angular coordinate, as theta. And so when we're dealing with angular things, angular concepts, we're going to be using radians now as opposed to degrees. All right, so let's say an object, a circle, maybe a disc or something like that, rotates a certain amount. Well, that certain amount, if we could like put a pin on the edge of that disc as it rotates, the amount that it rotated by would be our delta theta. And so if we could track that delta theta, that change in its position over a certain amount of time, that would give us our angular velocity. Remember, change in position over change in time is velocity. So now we're just taking that from a linear way of thinking into a circular way of thinking. So angular velocity is that variable omega, looks like a curly W. And so since that's a, kind of like an angle over a certain amount of time, the unit is radians per second. Angular acceleration tells us how that angular velocity is changing with respect to time, which is also related to how that position is changing. And so I wrote it here in terms of the derivative format. So instead of like delta theta over delta t, which would be your more algebra way to write it, the calculus way to write it would be d theta over dt to show that this is a derivative. It's a change in something with respect to time. Right? And so when we're taking the derivative of a derivative, we get this format of writing things, this second derivative. So the second derivative of our position with respect to time. Now, angular and linear kinematics are related to each other through the radius of the circle that it makes. Right. So the velocity, the linear velocity, is related to the angular velocity through this first equation, v equals r omega. The angular acceleration and the tangential or linear acceleration are related to each other through this relationship, r alpha equals tangential acceleration. And the radial acceleration or the outward acceleration is related to the radius and the angular velocity squared. Right, so if we're dealing with a constant angular acceleration, then we can use those same kinematic equations we saw in chapter 3 for a constant linear acceleration, but now we're going to kind of substitute in our angular variables. So everywhere we saw a position, now we'll put in theta. Everywhere we saw a velocity, now we'll put in angular velocity, omega. Everywhere we saw acceleration A, we'll put in angular acceleration alpha. So these are the same equations that we had in chapter 3, just using these new variables, but they're the same relationships. Moment of inertia measures the rotational inertia around an axis. So remember, inertia is the tendency to resist changing its motion. So the moment of inertia tells us about the tendency of an object to resist changing its rotation. We give it the symbol I. The unit is kilogram meters squared. And here's our formal way to calculate it. I equals the sum of all of the points of the mass at that point times the radius from the axis at that point squared. So we could have, like, let's say we were looking at 3 points on an object, right? We would have m1 r1 squared plus m2 r2 squared plus m3 r3 squared. Okay. So if we could sum up all of those points for a certain object, we would get its total rotation, moment of inertia, right? And similarly to our regular inertia, a bigger I value means it's harder to change the rotation. More inertia means it's harder to change the motion. And this time it depends not on the mass of the object, but how that mass is distributed around the axis of rotation. So on the next slide, I'll show you some like common shapes and how their mass is distributed with respect to the axis of rotation. And you can see the effect that it has on the equation for the moment of inertia. We also now have a new kind of energy to consider, rotational kinetic energy, right? Because as, let's say, a wheel is rolling, it's moving. So it has a kinetic energy associated with it. It's just, it's not necessarily sliding, right? It's not linear. Now it's rotational. But it's a very similar equation, right? Remember, linear kinetic energy is 1/2 mv squared, mass times speed squared. And now our rotational kinetic energy is 1/2 I, which depends on how the mass is distributed, times the omega squared, which depends on the velocity, right? The angular velocity. So it's a very similar idea. It's, again, we're just kind of substituting in our new corresponding variables. So here are those common shapes, and you can see the different axis of rotation for each one. So here's our solid cylinder. The mass is uniformly distributed. So our moment of inertia around an axis that goes through the center is 1/2 m, the total mass of the cylinder, times the radius of the cylinder squared. Now, if we have a hoop, now our mass is still kind of uniformly distributed around that ring, but there's no mass inside closer to the axis. So the farther away the mass is from the axis, the harder it is usually to make it start moving. Okay. If we have a solid sphere, again, our mass is kind of uniformly distributed around that axis of rotation, but in a different way than the cylinder is. So we have a different coefficient number out there, right? And so you can see, it doesn't just depend on the mass distribution either, right? We have a cylinder here on top and a cylinder here on the bottom, but our axis of rotation is different. Here it's going through the center this way, and on the bottom it's going kind of from the top to the bottom, so it'd be kind of spinning around this way instead. That makes a big difference in that equation for its moment of inertia, because the mass is distributed differently with respect to the axis of rotation. Same thing here, a rod rotated around its center. Here, I'll use the pen here. So a rod rotated around its center, you can feel a difference. Like if you have a pen or a pencil, you can feel a difference in trying to rotate the rod like this versus like this from its end. It's much harder to rotate it from its end because so much more of the mass is concentrated farther away from that axis of rotation. And so even though it's the same shape, we get a very different coefficient out there in front. So in Physics 1, you probably will be asked to derive some of these relationships. And so if you can kind of remember that idea of, the farther away the mass is from the axis, the harder it is to rotate, that can kind of help evaluate your answer. Okay. So from chapter 10, some more parallels between linear motion and rotational motion. And I know we're past 4:30 now, so if you have to go, it's totally fine. I won't be offended. But I am going to keep going. I want to go through this whole review with you so that it's in the video for you guys. Anyway, chapter 10, more similarities between linear and rotational. motion. So, right, in linear motion, we're dealing with forces, right, pushes or pulls that cause motion, a sliding or whatever kind of motion. Torque is is kind of the rotational analogy to force. It's a force that causes rotation specifically. So a torque gets that symbol tau, kind of like a curly little t there, tau for a torque. And this is calculated with a cross product. So a cross product is kind of the opposite of a dot product that we talked about with work. A cross product shows us how perpendicular two things are to each other, right? Whereas a dot product shows us how parallel two things are to each other. So when we're dealing with a cross product here, like torque is R, the position vector, cross F, the force, I like to think about it conceptually in terms of opening a door, for example. So let's imagine that this paper here is a door and like here's the doorknob. There's a reason they put the doorknob here on the outside of the door as opposed to like if you're a hobbit and the doorknob is in the middle of the door. And that's because we are lazy and we like to use the least amount of force possible. So if we want this door to rotate open, right, we want to apply the smallest amount of force to make it open. So we want the biggest the biggest distance from the axis. And then we're going to want to push on that door perpendicular to the door, perpendicular to this radius. Right? If you try to open the door by like pulling on the door sideways, unless it's a sliding door, it's not going to work out for you, right? If it's a rotating door on hinges and you try to pull it this way, it's not going to open because you're not applying a force perpendicular to that position vector. And similarly too, if you, like, let's say the hinges are over here, if you're pushing on the door close to the hinges, it's a lot harder to close the door than it is if you're pushing at the edge of the door. Right? You're getting less torque when you have a smaller distance from that axis. And so the more torque you have, the easier it is to apply a force. So that's why so I like don't fix cars. That's my husband's job. But I do know there's such a thing as a torque wrench. And let's say you're trying to tighten a bolt and your wrench is just not doing it. You can put a pipe on the end of your wrench to extend your wrench out farther, and then it becomes much easier to twist that bolt around, right? You decrease the amount of force that you need by increasing the distance, that position vector. Okay, so Newton's second law for rotation, you'll see, is very similar to Newton's second law of motion, like the linear version. It's just that now instead of dealing with a net force, we're dealing with a net torque. So if there is a net torque on something, there will be an angular acceleration. Right? It will rotate if there is a net torque on something. So if you are inside the door and you're trying to push it, and your friend is outside the door trying to push it the other direction, remember torque is a vector, the direction matters. If you're pushing with the same amount of force, the same amount of torque in the same place on the door, there will be zero net torque. And so the door will not change its motion. It will not rotate if there is no net torque. Right? If you push harder than your friend in the same location, then your force is increased, so your torque will increase, so the door will rotate open. Okay, very similar idea to our current understanding of Newton's second law of motion. A torque does work on an object the same way that a force does work on an object. And that work done is equal to the change in rotational kinetic energy, just like before we saw work is the change in kinetic energy. So now we have kind of revisited that work energy theorem, but in our rotational mindset. So here, work is torque times the angular displacement instead of force times the displacement, which again, we're relating that to the change in the rotational kinetic energy, 1/2 I omega squared. And again, power is the rate at which torque does work now. So power equals torque times its angular velocity instead of parallel force times velocity. Okay. Again, just like we had momentum, now we have angular momentum. And so angular momentum gets that variable capital L. We can relate that to linear momentum if we keep in mind the distance from that axis of rotation. So distance cross linear momentum. Linear momentum, remember, is mv, so we get r cross mv, which is the same thing as saying I times omega. So you can kind of see, again, those similarities there. I is the mass distribution. Omega is the angular velocity. So angular momentum is mass distribution times angular velocity. Linear momentum is mass times velocity. Very similar concepts here. So this equation, this I omega equation, is true if it's rotating around an axis of symmetry, so the center of an object, for example. And so to figure out which direction the angular momentum vector points in, because it is a vector, we can use a right-hand rule. Now, I didn't go into a whole lot of detail with you guys about right-hand rules. You'll see more of those in Physics 2. But for a right-hand rule, you must use your right hand, obviously. And so you curl your fingers in the direction that an object is rotating, and your thumb will point in the direction of the angular momentum. Okay, so curl fingers in the direction of rotation, your thumb points in the direction of momentum. Okay, so again, you'll see many more of those right-hand rules in Physics 2. Chapter 11 is all about equilibrium. So again, we sort of touched on this when we talked about Newton's laws and forces in chapters 4 and 5, but now we're adding a little bit of an extra bit to it now that we know about torque and rotation. So equilibrium, remember, it happens when an object is not accelerating. So an object can either be at rest, that would be static equilibrium, or it can be moving at a constant velocity. That's called dynamic equilibrium. And now there are two conditions that must be met to have an object be in equilibrium. And first of all, the sum of the forces must be zero. Right? No net force, no acceleration. That's Newton's second law. But now we have to consider the rotation of an object too. So if we don't want the object to be accelerating rotationally either, that means the sum of the torques around any point on that object must be zero as well. So there can't be any rotation either. So net force is zero and net torque is zero to have equilibrium. And so here at the bottom, I also gave you a way to calculate the center of mass, or the center of gravity, really, of an object. Because a lot of the time we're dealing with gravity as a force that causes a torque. And so if we can figure out where that center of gravity is, that can greatly simplify our problems. So off here to the side too, I show three different situations, right? So in this first situation, there is no net force because there's two forces up and two force down. So those balance each other out. There's a force that would cause it to rotate this way, but a same size force that will cause it to rotate that way. And so those cancel each other out. There's no net torque. So this first picture is in static equilibrium. It will not move. It will not rotate. In this second one, there's no net force because look, there's one F up, one F down. Those balance each other out. However, both of those forces, if you can imagine like a string attached to the disc where that force is, if you could pull that string, which direction would it cause it to rotate? Well, it will cause it to rotate around clockwise. If we could pull that other string up, it would also cause it to rotate around clockwise. So those two torques do not cancel each other out, they add together. And so this object will start rotating, which means that it is not in equilibrium because it will rotate. And this third example, we do have a torque pulling up like this. We have another torque pulling up like this. However, this 2F torque would try to cause it to rotate counterclockwise, whereas this F force would cause it to rotate clockwise. They do balance each other out, right? Because this distance where this force is applied is half the distance of this other one. Even though that force is twice as big, that 2F gets canceled out by that 1/2 L. And so these two torques are actually the same size, but these two forces are both pointing upward, so they will not balance each other out. And so this object will not rotate, but it will move upward. Okay, so one example of yes equilibrium, two examples of no equilibrium. And then chapter 12, we talked about gravitation. So Kepler's 3 laws of planetary motion. His first law, planets move in elliptical orbits, not circular orbits, with the sun at one focus. Remember, an ellipse is kind of like an oval. Now, the planets do have very close to circular orbits for the most part, but they're not perfectly circular orbits. And Pluto is the most elliptical of all of them. Well, all of the planets. Poor Pluto. So it was demoted. Kepler's second law tells us that an imaginary line from the sun to a planet sweeps out equal areas in equal time. So as the planet is orbiting around the sun, it will not go at the same speed in each point of its orbit because these orbits are not perfectly circular. So that means at some points in its orbit, it will be slightly closer to the sun than at other points of its orbit. Right? So when it's closest to the sun, that's called perihelion. And when it's farthest from the sun, that's called aphelion. And so since it is closer to the sun at perihelion, that means the force of gravity is slightly stronger there. And if we have a slightly stronger force, we have a slightly greater acceleration, right? So it will move a little bit faster when it's closer to the sun than when it's farther away from the sun and the force of gravity is slightly less. And so since it moves slower over here on this side, but then faster over here, if we look at, let's say, 1 month interval, for each time interval, it will sweep out an equal area, kind of triangular shape, but like a pie shape, right? A little bit rounded over here. So it will sweep out equal areas in equal time intervals because it moves faster sometimes and slower other times. Kepler's third law relates the period of the planet, so how long for one orbit, and their distance from the sun. And so basically, the farther away it is from the sun, the longer it takes to complete one orbit. So he gave us the relation t squared orbit squared equals, period squared equals that distance from the sun cubed. Now, Newton later edited this a little bit to include the mass of the sun here. So we can see that proportion is still there, but now we have this kind of other factor out in front. Newton's law of universal gravitation tells us now about how the force of gravity acts not just near the Earth, but for anywhere, any pair of objects. We have this big G, which again, I should have written it down. I didn't. I'll add that before I put this up on Canvas. But remember, big G is 6.67 times 10 to the negative 11. That is a constant. And then we have the masses of the two objects and that distance between their centers. Now this R must be between their centers, not their surfaces. That's important. But basically this tells us that you would have to be infinitely far away from something to be totally free of its force of gravity. Okay, and we can't really do that. The acceleration due to gravity is big G times the mass divided by the distances squared, right? Because F equals ma. So A equals the force divided by a mass. So force divided by mass 2. Gravitational potential energy, we have to revisit this because now we are not necessarily near the surface of the planet. We cannot necessarily choose a convenient 0 point anymore. Our 0 point is at infinity. Right, so our new way to calculate the gravitational potential energy is negative big G times the masses divided by the distance. And then we talked about the speed of a circular orbit. We talked about the escape speed. I'll add that in here too. Then we talked about the period of a satellite in a circular orbit. Okay, so here we are 2 example problems that would make great final exam problems or midterm type problems. So example 1, a ski jump. A skier wants to land exactly 14 meters from the bottom of a 9-meter jump, so 9-meter tall jump, at 35 degrees. At what height should he start with 0 initial speed? Okay, so we're dealing here with a problem that combines projectile motion, right? And the easiest way to do this is energy. So I would recommend for this problem that you start at the end and think about how fast he has to be going at the end of the ramp to make it 14 meters. Right? What is this initial velocity to give him a distance of 14 meters? And then once we figure that out, we can switch gears to energy and think about, well, to be going that speed at the end, how fast does he need to be going? I'm sorry, how high does he need to be at the start? Okay. So first we're going to start with our projectile motion equations here. We know these two relationships, you see the equations are similar, but we're instead of, well, we can't combine our directions, right? So we have to keep our x direction and our y direction separate from each other. So everywhere in this first equation, every variable is dealing with the x direction except for time, because remember, time is that linking variable between the two. And we're dealing with separately the y direction. Sorry, my daughter broke in. We're dealing with the y direction separately. Okay, so everything in this second equation is y direction. Okay. We also are dealing with a ramp that's at an angle. So we are going to need to take our initial velocity and break it into its components using that angle that we know. Okay. So since our angle is 35 degrees, the cosine of 35 degrees is 0.819 times our initial velocity. And in the y direction, we're dealing with the sine of 35 degrees, which is 0.574 times our initial velocity, right? So now we have the x component and the y component of that initial velocity. So since we have those velocities, we can plug those into our kinematic equations that we have here at the top. So we know our change in x distance or position is 14 meters, right? So we put 14 in there. Our v0x, the x component of our initial velocity, we just found using the angle to be 0.819 times v0. We multiply that by the time, which we don't know. And remember, in our x direction, if there are no forces in our x direction, if we're ignoring air resistance, then our x acceleration is 0. Okay, there's no forces to cause an acceleration. In our y direction, he is going to be falling down 9 meters. So our change in height is -9. Right, v0y we found from our angle to be 0.574 times v0 times t. And in this case, in the y direction, we do have an acceleration. That's the acceleration due to gravity, -9.8. Remember, negative because it's pulling down. Okay. So we have those two equations, which you can see they both relate to v0 and to t. So now we have kind of two linking variables between the two. v0 we can get most easily from this top equation, right? 14 divided by 0.819 will give us v0t. So v0 is 17.09 divided by t. And then we can use, we can plug this in to our bottom equation where we see v0, right? So we can get, simplifying that, we can get the time that it takes, 1.96 seconds. Now, they didn't necessarily ask for the time, but it is helpful to know because now that we know the time, we can plug that back into our x equation and solve for v0 to get 8.72 meters per second. Okay, so that means that at the bottom of the ramp here, like when he leaves the ramp, he must be moving with an initial velocity of 8.72 meters per second if he's going to make it 14 meters. Okay, so now thinking about how high he needs to be at the start, we need to ask ourselves, what kind of energy do we have at each point? So what kind of energy are we dealing with at the beginning where he's starting? And what kind of energy does he have at the bottom of the ramp? Okay, there's no outside work for us to consider. We're ignoring friction, we're ignoring air resistance, energy is conserved, which means our change in energy is 0. So our initial energy equals our final energy. Now, initially, we're told that he's moving with 0 initial speed, so he does not have any initial kinetic energy. Okay, it's all just due to his position above our reference point, which is the ground. So our gravitational potential energy, since he's near the surface of Earth, we can use our kind of simplified equation, mgh. At the end of the ramp, he's still above our reference point, so he still has gravitational potential energy, but he's also moving, so now he also has kinetic energy, right? So mgh, this time the h is the height of the ramp, plus 1/2 mv squared. Now we just found that velocity that he's going, so that's really going to help us here. But you can see in each of those terms, we have a mass, so we can cancel those out. We don't need to know how much his mass is. So g times his initial height equals g times the height of the ramp, 9 meters, plus 1/2 our velocity squared. That gives us an initial height of 12.88 meters. Whew, it's a big problem. Lots of things going on in this problem, but actually this is a very like engineering type of problem. So if you plan on becoming an engineer, then customers will often say to you, I want this. I'll pay you $100 million to figure out how to get there. And then you have to figure out how to get to that ending product or that end result that they want, right? And so often you'll have to start at the end and kind of work your way backwards. Example 2, a roller coaster loop. What is the minimum height of the roller coaster's car starting position such that it gets around the loop safely. Okay, so here we're combining energy with circular motion because now we're dealing with a loop. So again, we're going to begin at the end because we don't know that initial height, but we do know more information about the end. So we need to know how fast it needs to be going to get around the loop, just barely get around the loop. And then given that speed, where does it have to start to have that speed as it starts the loop? Okay. So let's look at just this loop here and think about what forces are present. Now we know we have the force of gravity pulling down because we always do when we're close to the surface of the earth. Centripetal force is a direction of a force. Centripetal means towards the center of a circle. It is not a kind of force that you would draw into a free body diagram. It is a direction of a force. Okay. And then normally we would have the normal force here as well. But if we want the case where it just barely makes it around, right, the minimum height needed for this car to make it around the loop, then our normal force would be 0. So we're just dealing with the force of gravity. Okay. But here, the force of gravity is directed toward the center of the circle, so it is a centripetal force. So our centripetal force equals mass times centripetal acceleration. We saw earlier that a centripetal acceleration is v squared over r. Okay. So our force of gravity is mass times v squared over the radius of the loop. Okay. We know the force of gravity is mass times g. And we can see here that on both sides of the equation, we have a mass, so that will cancel out. So g equals v squared over r, which means the velocity at the top of the loop is going to be the square root of g times r. Well, g is 9.8, r is 8. The square root of 9.8 times 8 is 8.85 meters per second. Okay, so that's how fast it will be going right at the top of the loop. That's the minimum speed it needs at the top to make it around the loop. Now, we need to know how high it has to be to have that speed at this point, at this height. Okay. So again, we're not considering friction or air resistance. This is an idealized case. So there's no outside work that will change the amount of energy we're dealing with. So our initial energy equals our final energy. Initially, this car is at rest, and we can see that from our picture. So there's no kinetic energy at the beginning, just potential energy gravitationally. At this point, though, not at the end, but at the top of the loop, it is moving, and it is above the ground, our reference point. So it has both kinetic and gravitational potential energy. Okay, so now we've set up a problem very similar to example 1. We can see that we have a mass in each term, so that cancels out. G times the height, the minimum height needed, equals 1/2 times that velocity squared plus g times that height of the car at that loop. Okay, g is 9.8. Velocity we found to be 8.85. And if the radius of the loop is 8 meters, that means the height of the car at the top of the loop is 16 meters. So that gives us a minimum height of 20 meters for this car to roll down, make it safely, just barely make it safely around the loop and continue going. Okay. All right. So do you guys have any questions about this review or about the class? If you do, please do let me know. I'm going to stop the recording with this last reminder to please take the post-test as soon as you can. Try to do it by sometime this weekend. That would be really helpful to me. But it's been an honor and a privilege to be your teacher. I hope this class has been helpful to you. And of course, if you have any questions, even during your semesters at FIT, you have my email. Feel free to reach out. And I wish you guys the best of luck. Bye.